Hey everyone, welcome to 3 Eco 309. In this video, we're gonna go over the first chapter in our course, which is a review of the statistics. We are skipping chapter 1, which is basically introduction to economics forecasting. So before the review, I do want to give you a general introduction to economic forecasting, so that you have some idea about what we're going to learn in this course. So economic forecasting is basically a big series of tools used to do forecast for different economic or financial variables. For example, it is very important for the business to forecast its future revenue or future sales in preparation for current stocking or current production. It is also a popular tool to forecast for future GDP from a macroeconomic perspective. And I'm not sure if you know this or not, the Federal Reserve usually will release forecast for future GDP, like GDP in the next quarter, GDP for the rest of the year, our employment forecast. So all those forecasts will help business better prepare for what's coming up in the future. And the techniques used there include economic forecasting, the tools that we will learn in our course. And of course, this is only introduction to economic forecasting. The techniques used there are more complicated, but it's still based on what we learn in our course. All right, so overall, in one sentence, what we're doing in this course is using tools to analyze data to forecast for the future. Okay, so now let's return to the review of statistics, which is basically what you should have learned in Eco 302, the statistics course. And I want to start from population versus sample. And it's really, this is the basic of everything in statistics. The basic idea is that in real world, we are interested in certain population, but the problem is we can't access the whole population, and therefore we have to take sample. Hopefully the sample will represent the population well enough for us to be able to use the sample to make inference about the population. All right, so for example, suppose I'm interested in the jobs that our students find after graduates from the business school of Texas A&M Commerce, right? And I want to do a survey. I want to survey our graduates and ask the kind of job they found, the salary level they got, etc., right? Ideally, I want to survey every graduate from the College of Business. However, in reality, that's not possible. Some graduates are just not reachable. Some will not return the survey. And therefore, I will end up with a sample of the graduates from College of Business. And my hope is that those who responded to my survey are representative of the whole population, that is all graduates from College of Business, and then I can use their number to make inference, or in other words, get the general information about the whole population. That is all graduates from College of Business. All right, and because the sample only represent the population, but not exactly the same as the population, when we use the sample to make inference about the population or form some idea about the population, we need some tools to connect these two, because after all, the sample is not really the population. So in statistics, everything is related to how we can go from the sample, build the bridge, and move to the population. Is our sample mean, for example, close enough to our population mean so that we can use it for decision making? How good our sample mean can represent the population mean? So to answer all of these questions, we do need the statistical tools to make the inference and to help us to make better decisions. All right, so that's the basic concept or basic ideas of using statistics, okay? So what is population? What is sample? I'm sure everyone has some idea about these two concepts, right? So basically the population is the collection of all possible individuals that we are interested. Usually anything related to the population is assumed to be unknown and thus cannot be calculated. If we know the population, then we don't need statistics. You can go ahead, measure the population, make a decision right away. The situation when we need statistics is that we don't know the whole population. So we have to use sample. And therefore the sample is just a proportion or part of the population that we're interested. We have access to the whole sample, and we can also calculate things about the sample. For example, sample mean, right? Now, correspondingly, when we describe the population, we call it parameter. So population is associated with parameter. A parameter is a measurable characteristic of a population. Like population mean is the average of the whole population, although unknown, but could be the one that we're interested. Now, the corresponding term for sample is statistic, right? It's singular because it's one measurable characteristic of a sample, okay? Again, for example, the sample mean, which is the average of the whole sample, and we can calculate the average of the sample. Therefore, it is known for us. Let's talk about a few of the sample statistics and see how they are calculated, since we can calculate them using the data. Starting with sample mean. Sample mean is very simple. I'm sure everyone can do it. It's just simply the average of all values in the sample. What you do is you add up all the values and divide it by the number of sample values, or we call it the sample size, right? So in terms of the formula, it is equal to the sum of all values denoted by X and divided by the sample size denoted by N. I want to point out that we usually use X bar to denote the sample mean. And there's also a notation here that you may have learned before, but just a review, this sign here is called sigma. And whenever we see the sign, it basically tells us we are adding things up. Since sigma is followed by X, that means we're adding all X values up. That is, adding all values up in the sample, right? The next sample statistic we want to talk about is called sample variance. Sample variance is denoted by S squared, okay? And the formula shows us that sample variance is equal to the summation, meaning, again, we're adding things up. What we're adding up is actually the difference between each of the value in the sample minus the average of the sample, which is X bar. Then with that difference, we square it, okay? And instead of dividing by the sample size, we divide by sample size minus 1. There are more to say about this formula, but since this is a review and our focus is not really learn everything about the sample variance, so I'm gonna skip that. Just to mention that this n-1 is called degrees of freedom. So it's very special for sample variance. The denominator is n-1, and the numerator is the difference between the value in the sample and the sample mean squared and adding the squares up. All right, and when we have sample variance, we have sample standard deviation, which is basically the square root of the sample variance. And let's take a look at a very simple example. So in the example, we have the collection of people's ages, 23, 38, etc., all the way to 35. We have 10 of them. And we want to use Minitab to find out the basic statistics. What you see here is the output from Minitab. It shows the variable name, it shows the sample size, shows the mean, standard deviation, minimum, median, and maximum. Also the quartiles, which we will not go over in our course. Okay, so now what I want to do is, actually I want to show you the next page, then we're gonna move to Minitab, and I want to show you how to find out these results using Minitab. So the next page is a graphical summary of the data. On the left-hand side, you will see this graph, which is we call histogram. It shows the distribution of our data. Basic means in terms of ages, we find more people with ages between around 40 and some around 50 and 60, and more around 20, some around 30. So this histogram tells us how the ages are allocated or distributed. On the right-hand side, you will find a lot more details than what we've seen, but basically we can still find out the mean, standard deviation, variance, the three basic statistics we've talked about so far. All right, now let me go to Minitab and show you how we can obtain the results. So there we go. So this is the Minitab. When you open Minitab, you will see an empty spreadsheet here. What I did is I typed in the data. So I typed age 23 or 38. You can do that yourself as well on your Minitab. And if you want to follow along, you might want to stop the video or pause the video actually. Type in the data before you proceed, okay? So now assuming that you have your Minitab ready, let's get started. We will first go to Stat. On the top here, click on Stat, and the first one you will see is called Basic Statistics. And on the pop-up drop-down window, we want to pick Display Descriptive Statistics first. If you click on that, you will see a pop-up window like this, asking you which variable you want the descriptive statistics. And what you can do is to double-click age. Age will be filled in this box automatically. And click OK. Then we've got the descriptive statistics we saw a moment ago with the mean, standard deviation, and minimum, maximum, right? So that's the descriptive statistics. If we want the summary graphical results, we go to Stat again, click on it, go to Basic Statistics, and you want to click on Graphical Summary. Similarly, the variable we are interested will be age. So you double click age and age will appear in the box. Click OK. Then you will see the same graphical summary as we just saw on the PowerPoint slides. The same histogram, same numbers on the right-hand side. All right, so now let's return to the PowerPoint slideshow and continue. Okay, so the next topic we want to talk about is called the normal distribution and t-distribution. So these are the two widely used distribution, especially the normal distribution. It's virtually the basic of every distribution. But first of all, what is distribution? What are we talking about here? So distribution basically means the allocation of our data. And we will say this allocation of either the sample data which we can access or the population data which we have to assume to be distributed in a certain way, right? For example, if we were to talk about people's height, right? The common sense tells us that most people are around the average. Some people are very tall, and there are people who are not so tall or relatively short, right? But most of us are around the average. And that actually is a perfect example for normal distribution, meaning that most people have a height of around the average. Some are very high, some are very short. Okay, and it just tells us how the people's height are distributed or allocated along the line. Now for normal distribution, if you look at the graph on the right-hand side and focus on the green curve, okay, that represents a normal distribution, okay? And you can see for normal distribution that it is bell-shaped, it is symmetric. It just means that most of the values are surrounding around the mean. Some values are very high and some values are very low, okay? That's what we call the normal distribution. Although the notation here you see is a Z distribution. So Z distribution is actually a very special distribution within the family of normal distributions. It's called standard normal distribution. With standard normal distribution, the mean is actually 0, the average is 0. Apparently that cannot be true for people's height. For people's height, the average will be, I honestly don't know, I'm just kind of making numbers up. I would think maybe the average height for women is around 5'8". I could be wrong again. And then, but for standard normal distribution, the mean is 0. The standard deviation is 1, and we call that Z distribution. The other distribution that we do need to know is called the T distribution. T distribution actually is very similar to the standard normal distribution in the sense that for T distribution, the mean is also 0. And the shape of the T distribution is actually controlled by something called degrees of freedom. I do not intend to talk more about it. It's a term. And if you know it, that's great. If you don't know it, it takes time for people to understand it. I'm sure you can survive Equal 309 without really totally understanding degrees of freedom. Right, so that's T distribution, very close to normal distribution, but serves different purpose. There are situations where we're gonna use normal distribution. There are other situations where we're gonna use the T distribution. Okay, and by the way, you may ask, well, the example you gave me is about people's height, and apparently the mean there is not 0. When do we have a distribution with 0 mean? Honestly, rarely. But why do we talk about standard normal distribution and T distribution? Well, the reason is that a lot of times, you know, when we deal with data, we need to manipulate data. We need to do multiplication, division, summation, subtraction, addition, etc. Right? When you do those manipulations, apparently 0 is easier to work with. We all like 0. 0 times 0 is 0, right? And therefore, even though sometimes we have normal distribution where the mean is not 0, we will eventually, we do have a way to convert that into a standard normal distribution and to make the mean 0 so that's easy for us to manipulate, to calculate. And by the way, that's the formula to do that. This is pretty much outside our discussion, the scope of discussion, but just for your information, right? It's kind of jumping, but the next topic we want to talk about is called inferential statistics. Okay, What is inferential statistics? Well, this is more advanced statistics than just getting the mean, the variance, or the standard deviation of a sample. Inferential statistics is a decision-making process. We want to use the sample data to make a decision about a population. And that decision could be to estimate for the population or to predict for the population. There are two tools. The first tool is called confidence interval, and the second tool is called hypothesis test. Okay, and we will go over each one, and these two are very important. We'll use these two again and again in the rest of the courses. So it's very important that you review this carefully and make sure you understand it. I do have to say that hypothesis is not easy to understand at the beginning. It takes time for you to follow the idea there, to follow the thinking process there. But once you get it, it will make sense for you. All right, so I want to start with the easy one called confidence interval. The idea is that, say for example, we're interested in a population average. Okay, as I said, we can't access the whole population, so we have to draw a sample from that population. From the sample, what we can get is just the sample average, right? Can we say that the sample average is equal to that population average we're interested? The answer is no, because it's, again, just a sample. How representative it is, we don't know. Even we got a representative sample, is not completely the same as the population. And I can guarantee you that if you do an experiment, write random numbers on a piece of paper, right? Write 100 of them, put in a box as your population, draw 30 of them or 40 of them, calculate the sample average. That average is unlikely to be the average for the whole population. That is the average for the 100 numbers out there, okay? And therefore, it is not really a good idea just use the sample average as if it were the population average. We call the sample average point estimate because it's just one number. It's one point along the number line. Okay, it is a single value derived from the sample. And it is not equal to the population value. Okay, 99.99%, the sample average is not equal to population average. Okay, so if we just use the sample average to make a decision, we could be wrong a lot of times. A solution for that is called confidence interval, which is a range. Instead of estimating the population average using a single number, we want to use a range to estimate the population mean, or population parameter, could be population variance. And with that range, we hope that the population mean is in it. And with the method used, discussed here, that range will be likely to include that population mean. Okay, it's not a random range. It's a range that we can be sure that the population mean is in it with a very high confidence. We can't say 100%, but we are very confident that the population average is within that range. How do we construct that range? Well, we have a formula here. The CI stands for confidence interval, is equal to the point estimate we have been talking about, which is the average from the sample, plus or minus a margin of error, meaning that we realize the sample mean is not exactly the population mean. But if we add a buffer or margin of error on each end of that sample mean, the range will most likely include that actual population mean. I know this is kind of abstract, right? So I've got more concrete formula for you to look at. Some of you may not like formulas because you studied, you use it, you do a lot of calculation. No worries. For our course, I will not ask you to actually use the formula to do the calculation. It's more for understanding. All right. So how do we construct a confidence interval for a mean? Again, we're interested in the population mean, and we want a range for that mean. How do we calculate that? Well, we start with the sample mean. We draw a sample, we get a sample mean. From the sample mean, we add and subtract a number, and that number is calculated by a z-value times the standard deviation divided by square root of the sample size. Okay, that z-value comes from the standard normal distribution. Again, I do not intend to go beyond there, okay? If you learn this and you still remember, but that z comes from the standard normal distribution. Standard deviation comes from the population, if we can get it. Sample size comes from the sample. And if we assume the standard deviation to be known, we use the standard normal distribution. If we can't know it, we have to use the sample standard deviation and we use the t-distribution. Okay, it's just the basic idea of calculating confidence interval. All right. A quick example just to show you how exactly this interval is calculated and what the interval tells us. So it says here, a tire manufacturer wishes to investigate the tread life of these tires. A sample of 10 tires driven 50,000 miles reviewed a sample mean of 0.32 inch of tread remaining with a standard deviation of 0.09 inch. Construct a 95% confidence interval for the population mean. Would it be reasonable for the manufacturer to conclude that after 50,000 miles, the population mean amount of tread remaining is 0.3 inches? All right, so from the problem, we can find that the sample size is 10. The sample average 0.32 because out of the 10 tires driven for 50,000 miles, there's an average of 0.32 inch of tread left. Standard deviation is 0.09, which is the S in the formula, and we're gonna use that formula to do the calculation. Okay, so we can construct the interval as the following, plug in the numbers, going through the calculation, eventually we got this range, 0.256, and the higher or the upper end is 0.384, which basically means, okay, the average amount of tread remaining for all tires after driven for 50,000 miles. It should be between 0.26 and 0.38 inches. Okay, so that's the average amount of tread remaining for all tires after driven for 50,000 miles. Okay, and this is the range for the population average. Again, all tires. All right. So what we can tell from the interval is that on average, if you purchase a set of tires from the manufacturer, you would expect the remaining trend to be between 0.25 and 0.38. Now, if you got the number that's outside that range, especially towards the lower end, there's a problem with it, right? You would question the quality of the tires. The question asks whether it's reasonable to claim that the mean amount of tread remaining is 0.3 inches after 50,000 miles. How can we find that out? Now, well, the mean amount remaining is the population average. And we're asking whether it's reasonable for us to say that the population average is 0.3. Now, based on the interval, 0.3 is within the interval. So it is possible, right? With the interval, it tells us the population average can be anywhere between 0.26 and 0.38. 0.30 is within that range. So it is reasonable to claim that the mean amount remaining is 0.3 after driven for 50,000 miles. All right, so that's the example for the confidence interval. Now we're moving to a tougher task. It's called hypothesis test. So the basic idea about hypothesis test is to compare the population parameter. Again, I'm gonna use population mean as my example. To compare population mean with a specific number to determine whether that population mean is greater than, lower than, or equal to that specific number. Okay, for hypothesis test, what we are doing is basically checking if a statement about the population mean is correct or wrong. And we have two hypotheses or two statements. One is called the null hypothesis, and the other one is called the alternative hypothesis. Okay? Why do we need to? For the sake of argument, if you say one statement is wrong, then you propose an alternative and say, well, then the other could be correct. That's the idea of getting two hypotheses, and they complement with each other. For the null hypothesis, we have special requirement. It is a statement about the value of a population parameter, and we use it as an assumption. We usually assume a null hypothesis is true. Then we draw the sample, we get evidence to determine whether the assumption still holds or not. If the assumption holds, then we claim that the null hypothesis is true. If the statement doesn't hold, then we will say the alternative hypothesis is actually supported. So what is the alternative? Well, the alternative is a statement that we need to use the sample to verify if true. Or in other words, we want to look for evidence in the sample that is in support of the alternative hypothesis. If we find enough evidence in support of the alternative hypothesis, we say the alternative is supported, and we have enough evidence to conclude that the alternative is true. Otherwise, if we can't find enough evidence in support of the alternative, we will go back and say the null hypothesis is true. Okay? And to perform the test, actually, we do need several steps. We start with setting up the hypothesis. That is, you need to specify the statements you want to test. And then you select the level of significance. The level of significance, basically, you can think of this as the accuracy of your test. How accurate you want your test to be. And there's trade-off. You want your test to be more accurate towards there's also this tendency for you to make the other type of mistake. We'll talk about this more in a minute. Then in the third step, we want to identify the test statistic, which is basically evidence from the sample. We gather evidence from the sample. Step 4, we form a decision rule. That is, we decide under what condition we will say the evidence is strong enough, or we have enough evidence in support of alternative. Then in the last step, we have a sample, we go through the steps, and we make a decision whether we have enough evidence in support of the alternative or not. Okay? And the decision is basically either reject the null, say the alternative is supported, or do not reject the null hypothesis and say the alternative is not supported. Typically, when we perform hypothesis test, our desire is to find enough evidence in support of the alternative. Sometimes we do, sometimes we don't. It just depends on the nature of the question and the data we have. All right, so for the null and the alternative, to simplify, we have notations for both of them. For the null, we use H0. For the alternative, we use H1, okay? For simplification purpose, for the null hypothesis, we always have an equal sign. And then for the alternative, we'll have less than, greater than, or not equal to. This is really just to simplify the process of proposing the hypothesis, okay? So for example, again, we're interested in the population average, and the statement we have could be, we assume the population mean to be equal to 200, okay? And the alternative is we have certain suspicion that the population average may be greater than 200, and we want to find out which is true. Or we could say we assume the population average is 200, but we have some suspicion that the population may be less than 200. And again, we want to take a sample, look into the sample, and see if we have enough evidence in support of the alternative. And the last scenario is we're testing to see if the population mean is different from 200. So we have three scenarios in terms of the hypothesis. Most of the time, we are, at least in our course, most of the time, we're dealing with the last scenario. All right. Now here's what I meant by saying determine the level of significance or determine how accurate our test is. So if you look at the table, this is the basic idea. For the null hypothesis, right, is our assumption. There could be two states. The first one is that null is actually true. And in terms of us, but we don't know whether the null is true or not. All we can do is really rely on the sample data to determine if we have enough evidence in support of the alternative or not. And based on that, we will form our decision, either reject the null or do not reject the null. Now, if the null is actually true, but we decide not to reject it, then we make a right decision. We didn't reject a true statement, which is the right way to do. However, if we decide to reject the null just based on the sample evidence, and that could happen because we can't access the whole population. Based on the sample, we somehow decide, you know what, the null statement is not true and reject it. But actually the statement is true, then we're making a type 1 error. Okay? And we also have another type of error called type 2 error. This is the situation where actually the null statement is false, but based on the evidence from the sample, we'll fail to reject that, or we fail to recognize that. And then we are making a type 2 error. Okay. Lastly, if the null hypothesis is actually false and we decide to reject it, we make a right decision. So during the whole process of making judgment based on the sample data, we could potentially make two types of mistakes, type 1 error and type 2 error. With type 1 error, we are rejecting a true null hypothesis. With type 2 error, we fail to reject a false statement. Okay. Now there's trade-off between the two. If you say, well, I want my test to be very accurate. I want to minimize type 1 error and type 2 error. Yes, to a certain extent, you can do that. But once you go beyond a certain range, if you decrease type 1 error probability, you actually will increase the probability of a type 2 error. So when there's trade-off, you will need to decide, or actually we will need to decide which type of error you want to focus? Do you want to really minimize type 1 error all the way to the end, or you want to minimize type 2 error all the way to the end? Well, to make that decision, we need to ask, which type of error is more serious? Okay. It turns out type 1 error is more serious. So we want to control type 1 error as a priority. And at the same time, of course, we want to minimize type 2 error as much as we can. Just to give you a simple explanation, hopefully, as to why type 1 error is more serious. You can think of this whole judgment as a trial, right? We have a suspect committed a crime, potentially committed a crime. This, of course, the suspect will not tell the truth. So we need to go get evidence to determine if the suspect is guilty or not, right? In the whole trial process, we always assume, so we have this philosophy saying that innocent until proven guilty, right? We always assume everyone's innocent, then we try to prove this person's guilty. We look for evidence to prove this person guilty, right? And type 1 error basically means an innocent person was wrongfully accused, right? Because you reject the true null hypothesis. You reject the assumption of innocence. And therefore, that means an innocent person basically is wrongfully accused and thrown into jail, right? That is considered more serious than the opposite, where a guilty person is set free. Well, that's how the law goes. And therefore, we're going to try to control type 1 error more than type 2 error. The probability of committing a type 1 error then is called level of significance. That's why in the steps, we select a level of significance. In other words, we select the probability of committing a type 1 error when we make the decision. And our decision is to minimize that. Therefore, for level of significance, we usually pick 1%, 5%, or 10%, meaning that when we make a decision based on the sample data, we have only 1% of making a mistake, a type 1 error. All right. So when we go through the process, right? Set up the hypothesis, select the level of significance, we'll talk about that. Next thing is the test statistic and the decision rule. Well, what is test statistic, first of all? Test statistic is actually a value calculated from the sample. And we use that value as evidence to determine whether the alternative hypothesis is supported or not. Then we can say whether we reject the hypothesis or not, okay? So you can kind of take the test statistic as a summary from the sample data that allows us to use as evidence in support of the alternative. Whether that test statistics is strongly supporting the alternative or not, we need to look at the decision rule. There are two decision rules. One is called critical value. Not big fan of it, and actually I do not intend to go over the critical value. I would rather we go over another decision rule, which is called the p-value. That's much easier to use and actually more relevant for our course, okay? So again, test statistic is the evidence from the sample to determine whether the test statistic is, as the evidence is strong enough in support of alternative. We need to look at the decision rule, which is the p-value. And I know if this is the first time you're learning hypothesis test, or even you've learned this a long time ago and you're doing the review, what I've talked about so far is probably not connecting yet. Hopefully, after going over this example, you will have a better idea of what is going on with hypothesis test. So it says here, a drop shop foreman thinks the mean weight of parts produced by a certain machine has decreased. It is desired to test the hypothesis that the mean weight of parts produced by the machine is still 50 pounds, the mean weight of the parts in the past years. A random sample of 100 parts is taken. It is assumed that the standard deviation of part width is 5 pounds, regardless of the mean weight, since this value has remained constant in the past studies of parts. Suppose that the sample mean turned out to be 48.6 pounds. We want to know if the sample mean is far below, we want to know whether this drop shop foreman's opinion is correct or not. And you can take this as kind of quality control, right? If the average weight is supposed to be 50 pounds, then we want it to stay that way. And if there's certain doubts or certain thoughts saying that, well, the average may have decreased, then it's substandard, the quality is not maintained. We want to maybe fine-tune the machine to make sure the average is still 50. Of course, you don't want to measure every product from that production line, right? What you do is you take a sample. In this example, we have a sample of 100 parts taken from the production line, and we measure those 100. The average turns to be 48.6. It is lower than 50, right? But the question is, when you take a sample, the average can deviate from 50 to a certain extent, and we're still okay with that. If it deviates far away from it, then we will say there's something wrong with the machine. With 48.6, the question is that deviation high enough for us to be concerned about this whole production process, for us to be concerned about the machine? Is it low enough, this number 48.6, for us to say we need to fine-tune the machine? So that's the idea of testing the hypothesis right here. Now, since the suspicion is that the average may have decreased, the alternative statement is population mean less than 50, because that's what we suspected. Now, the assumption, though, is that we still assume the machine is acting correctly, the machine is still doing well, so that the average is still 50. Okay, so we want to test these two statements using the sample. And again, the sample mean turns to be 48.6. Okay. Now, as I said, the second step in the list is that we need to determine how accurate we want the test to be. We need to select the level of significance, which is the probability of type 1 error. The default level is 5%, and that is commonly accepted. Sometimes we'll pick it to be 1%, sometimes we'll pick it to be 10%. Let's just use 5% for our course, unless otherwise specified. If we pick 5% significance level, the significance level will determine the decision rule. In terms of the rejection region that we didn't talk about, this will tell us the threshold when we can say, oh, this is enough evidence, this is not enough evidence. But again, as I said, I want to move to p-value and focus on p-value right now. So what is the p-value? Well, p-value, I have to warn you at the beginning, is kind of difficult to understand at the beginning. But once you get used to it, you will love it. P-value will make hypothesis much easier. So the p-value is a probability, first of all. What kind of probability? It's the probability that describes how likely we can observe the sample if we assume the population in the null hypothesis still true. So let me reverse back to the hypothesis right here. Look at the null hypothesis and alternative. We're assuming the population means 50, but we suspect that the population mean may have decreased to be less than 50. And then we take a sample from that supposedly to be 50 population and look at a sample to determine if that population average has already decreased, okay? Now, if we assume the machine is acting correctly, and we assume that the population mean is still 50, okay? Then the p-value tells us how likely can we find a sample mean to be 48.6? Or how likely can you find a sample mean this low, not even 50, not 50 at all, or not very close to 50, right? So for example, if we assume the population mean to be 50, and I draw a sample, the sample mean is 49.9. I won't question it, right? I will say the population mean is still maintained at 50, and the sample is 49.9 just because it's due to randomness, right? I randomly pick a sample. There's small deviation across different units from the machine, okay? I wouldn't be concerned. If the sample mean turns to be even 49.5, I wouldn't be concerned. So the question is, should I be concerned when the sample mean is 48.6? Well, the p-value tells me that, okay? Again, the p-value tells me if the population mean is still 50, how likely can I observe a sample mean as low as 48.6? If that probability is low, that is, it's unlikely for me to observe a sample mean as low as 48.6 when assuming the population mean is 50, then I can say something is wrong with the machine. Okay? The sentence I just said is the key, and it's not easy to understand. So I want to repeat that one more time, okay, and slowly. So the p-value tells me how likely I will observe a sample mean as low as 48.6 if I assume the population average is still 50. Apparently this 48.6 is lower than 50, right? So I may suspect that the population mean has already decreased to be less than 50. All right. Now, if I find that the probability of observing this 48.6 is very small, when assuming population means 50, then I would have to question my assumption and say, maybe the machine is not acting correctly. Maybe the population mean has decreased to be less than 50. That's the idea of p-value. It tells me how likely can I observe this. If it's unlikely, there's something wrong with the null hypothesis. Okay, there's something wrong with the machine. If it's likely, then no problem. That just means even though the population means 50, it is still quite likely that I got the sample mean as low as 48.6. It is fine. Right, so that's the p-value, okay? We will not talk about how to calculate the p-value, but the p-value does use test statistic. That's our piece of evidence, right? When we use the p-value, as said, if it's unlikely to observe a sample mean as low as 48.6, we will reject our assumption. But the term likely, unlikely is very weak, right? Something I say likely, something I say that probability is low, you might think it's high. if I say that probability is high, you might say it's low, right? It's really personal perspective. And therefore, we need something that is more uniformed. And that is this decision rule. Okay? If the p-value or the probability is even lower than our significance level, then we say that probability is very low. In other words, it's very unlikely for us to observe a sample mean as low as 48.6. And therefore, we have to question our assumption and say our assumption is not holding anymore. And therefore, we reject that assumption. So again, if the p-value is even lower than the significance level, which is 5%, then we say it's unlikely for us to observe what we have observed. That means the assumption in the null is not true, so we have to reject the null hypothesis. So that's the rule. After practice, what I explained in a long time reduces to the following. Reject the null hypothesis if your p-value is less than 5%. And if you can't remember anything afterwards, this is something you absolutely need to remember. Reject the null if the p-value is less than 5%. Okay. All right, so what about the p-value we have for our example? Okay. Although we skip the calculation, but I can tell you that the p-value for our example is 0.0026. And I'm sure every one of us will agree this is an extremely small p-value, which means it is extremely unlikely that we will get a sample mean as low as 48.6 if we assume the population mean is 50. And therefore, we have to say this assumption is not true. It doesn't hold anymore, so we have to reject the null and say, well, you know what? The alternative is supported by our evidence. The alternative turns out to be true. Okay? So that's the whole process of hypothesis test. Highly recommend that you review this if you didn't fully understand. Again, we're gonna use the p-value again and again in the future. Very important for you to understand. Lastly, I want to talk about the relationship between two variables briefly, because later on I'm gonna learn regression. And in regression, it's basically investigating the relationship between two variables. So I have a couple of examples here to show you different scenarios of the relationship between two variables. Basically, when we look at the two variables, we ask, are they related? That is, if one is changing, whether the other one changes with it. And if you look at the first example, it's basically the cost, the age of buses versus maintenance cost. And by intuition, we know the higher the age, the higher the cost, because the older the bus, the more maintenance cost it will have, right? And we expect a positive relationship, which is showing in the graph here. You will see the dots form a upward trend pattern, meaning that these two variables are positively related. And we can also say that the relationship is strong because basically the scatter plot, in the scatter plot, the dots are forming a straight line and is going along that straight line very closely. In comparison, if you look at this example, is the auction price of a car, used car, versus, the odometer reading, the mileage on the car. And the idea is the higher the mileage, the lower the price will be, which is the case if you look at scatter plot. The dots form a downward trend, meaning these two variables are negatively related. They are also kind of strong because if you draw a straight line, most of the dots are close to that straight line, although there are a couple of them that are far away, like this one. In the third example, this is height versus salary, which means the salary versus how tall you are. And as a relatively short person, I don't want to see any relationship here, which is true because if you look at the dots, they are scattered everywhere, meaning that there's no relationship between salary and height. They are not at least strongly correlated. But again, it doesn't mean the taller you are, the more wage you get. But this, again, is one study. During my teaching of statistics, I actually saw another example where in that study, they do find out that height matters to a certain extent, and taller people do earn more salaries. I don't know what you think about. You may have your own opinion in terms of observing what happens around you. And to measure the relationship between two variables, we have a term it's called correlation coefficient, or the coefficient of correlation, same thing. So R measures how two variables are related to each other, and R ranges from -1 to +1. Okay, that's the range. The highest is 1, the lowest is -1. And the closer the value to -1 or +1, the stronger the correlation. If we have R equal to -1 or +1, that means these two variables are perfectly correlated, either negatively or positively. And if this R is closer to 0, that means these two variables are virtually not related at all. Like if I reverse back in terms of R, in this example, age of buses and maintenance cost, I would expect this R to be very close to 1. In this example, height versus salary, I would expect this R to be close to 0. In the last example, price versus odometer, I would expect R to be close to -1, but not as close as the first example. The first example, that R will be very close to +1. In the last example, R will be relatively close to -1, right? Let's see. One last example. In this example, I want to show you how to get the scatter plot. We will use the scatter plot a lot in the future. It says the sales manager of Copier Sales of America, which has a large sales force throughout the United States and Canada, wants to determine whether there's a relationship between the number of sales calls made in the month and the number of copiers sold that month. The manager selects a random sample of 10 representatives and determines the number of sales calls each representative made last month and the number of copies sold. All right. First of all, apparently this is a very old example because it's still talking about the sales calls. I know it's still made, but there are many more methods for sales. But anyway, we have the data on the left side, right here in the table. We have 10 people out there listed with the number of sales calls and number of copies sold, right? In the middle, you will see what we call scatter plot produced by Minitab. Shows us graphically the relationship between these two variables, and we do expect them to be positively related because the more calls you make, presumably the more copier you should sell, right? And if you look at the dots in the scatter plot, they do kind of follow a uptrend pattern out there. And then I'll show you in a minute how to get the scatter plot. The other thing we can also get using Minitab is the correlation coefficient, the R we were talking about. The R for our example turns to be 0.759, which is close to 1, not very close, but close enough for us to conclude that the two variables are positively related. In terms of calculation for the R, this is the formula. don't even worry about it. We are not really using this formula. It's a very fancy one in the sense that there's tons of calculation behind it. All right, so lastly, I'm gonna move to Minitab again to show you how to do the scatter plot and how to obtain the correlation coefficient, okay? All right, so I'm back at Minitab, and I want to let you know that all data files are available on D2L under each week's folder. For this example, the copier sold example, I would suggest that you download the data first, then you can go to this little icon there, open, and locate where the file is saved on your computer. For mine, it's under 309 in data files. For mine, all data files are here, okay? If you want to, you can download all the data file needed so that in the future, when you go to Minitab, you can go to the folder directly to find the one that is needed. The one that's supposed to be used is called copiers. So I will open that file within Minitab, click open. And that's the file, right? So 3 columns. The first column is, tells us representatives. Second column, number of calls. The third column, copiers sold. All right. So next, I want to show you how to get the scatter plot and also the correlation coefficient. For the scatter plot, you want to go to Graph and pick the first one called scatter plot. We'll only use the simple scatter plot. Don't worry about the rest. So click on OK. And we need to determine Y variable and X variable. They are not randomly assigned, okay? The Y variable will be the variable that depends on the other one. So for example, in this example, the more calls you make, the more copiers you sell, right? It doesn't go the other way. It doesn't mean the more copiers you sell, the more calls you will make. And therefore, the Y variable will be copiers sold because that depends on the number of calls you make, which is the X variable, okay? Usually, we call the Y variable the dependent variable, meaning it dependent upon the value of the other variable. And we call the X variable the independent variable because it's independent of Y. It depends on something else, maybe, but doesn't depend on Y. All right, so I'm gonna click on OK. And there we go, that's the scatter plot. I need to move this a little bit down so that we can see it. Right, so that's the scatter plot between copiers sold and calls. Next, if we want to find out the correlation coefficient, we will do stat, basic statistics, and move to correlation. Click on that. We will need to double click both variables because we want the correlation between these two variables. Click OK. Oops. I didn't copy everything in the output. I only copied this part, which is the correlations, and the coefficient is 0.759, right? You will see the same scatter plot coming up with a few more statistics like the correlation coefficient R, which is, you can come here directly for everything, but there are situations where you may just need the correlation, you may just need the scatter plot. For that case, you go to Graph and pick scatter plot. All right, so that's all I have for chapter 2, the review statistics. Email me if you have any questions. I will talk to you next time.